The focus of this video lesson is historical depreciation. Now, as you should have noticed in today's Flipgrid prompt, the data that models the depreciation of a car's value follows more of an exponential curve than a linear one. So we're going to be focusing today on how to create equations to model that depreciation. Exponential decay is when the value decreases by the same percentage each year. Now, note, before we were looking at linear depreciation. In that case, it was decreasing by the same amount, not percentage. Now, exponential depreciation can be modeled by the equation y is equal to a times the quantity 1 minus r to the power of x, where a is the starting value of the car, r is the percent of the depreciation expressed as a decimal, x is the time in years, and y is the value after x years. Example 1. The historical data shown for a used Chevrolet Corvette two-door coupe in good condition. Determine the exponential equation that models the data in this table. So this is the same data that you entered into Excel for your warm-up today. Let's go ahead and look at what that looks like. So for your warm-up, you were supposed to type this information into Excel. Now what we're going to do is create our scatter plot, which you likely already have. So we select both columns of our table, insert scatter plot. We right-click a point, add our trend line, tell it to be exponential, and we're going to display our equation and our r squared value on our graph here. Now, one thing you are going to notice is that by default, Excel always puts our exponential equations using base E. Now, if you remember from earlier this year, base E is the same as 2.718 approximately. It's our exponential constant. Remember, we created that by using limits. Now, what we want to do is we want to make this equation look like the form of the equation we saw in our definition for exponential decay. All right, so we know that every exponential equation can be written in the form y is equal to a minus 1 minus r to the power of x. So our objective here is to figure out what our r is and what our a is. So for right now, because this part of our equation with the e has our power of x, we're going to associate it with our 1 minus r. So we're going to say then for our equation here, which we have 25,922, and then we have this e to the negative 0.085 x, we are going to say our a is here, and our e to the negative 0.085 is going to correspond with this 1 minus r. So we're going to write 1 minus r is equal to e to the negative 0.085. Now, using a calculator, let's do our 0.085, we'll make it negative, and then we're going to click exponential, so our base e. And actually, I think it's going to be the reverse of that. Let's try that again. All right, 0.85 negative. It does not like that. So here's what we're going to do. We are going to use our Desmos calculator. If you have a scientific calculator, you should be able to type it in directly. So we have e to the power of negative 0.085. And let's make sure that's correct. Yes. And so we get here our 0.918. 0.918. Let's round to the nearest percent, so 0.92. So we're going to say 1 minus r is equal to 0.92. Now, let's solve this equation. So minus 1, negative r is equal to negative 0.08. Divide both sides by negative 1. So r is 0.08. So we're going to say then that there is an 8% depreciation rate. Now, the actual question being asked here is, what is our equation? And we want it written in this exponential form. So what we have here is y is equal to 25,922, and then 1 minus 0.08 to the power of x. Now, do note, mathematically speaking, this equation that we've written is identical to the one provided by Excel. It's just written with a different base. So we're not using the base e. We've converted it so that it is in the form that is preferred by the depreciation decay. So the cool thing is, though, this equation tells us a lot of information, right? A is the starting value of the car. The 0.08% is the amount it's losing value, the percent it's losing each year. And it's easier to see that information directly from this version of the equation than it is from the base E version. All right, so for example 2, same problem, but different question. What is the exponential depreciation percentage for the 10 years of car prices as modeled by the depreciation equation found in example 1? So we kind of already discussed this in example 1, but we know here that the car value is depreciating by 8% each year. So the car loses 8% of its value each year.